Welcome to Pharma Drama, the channel where we look at the science of healthcare and healthcare products. In this video, I want to explain one of the most basic concepts in understanding medicines. What is a crystalline material? So, if you're ready to find out, make yourself a cup of tea, sit back, and let's make a start. The first thing to say is that crystallinity is a concept that applies to materials in the solid state. Remember that all materials, unless they are pure elements, are made up of molecules. In medicines, most drugs are small molecular weight organic compounds, so these are what I am focusing on here. As molecules rise in temperature, they gain energy, and they use this energy to move about. The movement can be within a molecule, intramolecular, such as a vibration or rotation, or it can be of the whole molecule itself, where the molecule possesses kinetic energy. The amount of energy that the molecules possess determines which state the material is in. If the molecules have a lot of energy, they can move around a lot. Their kinetic energy is greater than the strengths of any bonds they might form with other molecules, so they move independently and we see the material as a gas. If they have less energy, they can start to form weak interactions with each other, but they can still move around, and we see the material as a liquid. Finally, when the molecules have little energy, they cannot move enough to overcome the interactions they experience with neighbouring molecules. They become trapped, and we see these materials as solids. Incidentally, when a material has no energy, so the molecules are not moving in any way, we say the material is at absolute zero. Absolute zero is the same for all substances and is equal to minus 273.15 degrees Celsius, which is minus 459.67 degrees Fahrenheit, or 0 Kelvin. Since an increase in temperature means an increase in energy, we see a material move from a solid to a liquid to a gas as it is increased in temperature. When a material changes from a solid to a liquid or a liquid to a gas, we say it has changed phase. These phase changes occur at specific temperatures, the melting point and the boiling point respectively. Crystallinity is a concept that applies only to the solid phase. The reason is that crystallinity simply means the molecules in a material are ordered into a repeating pattern. For there to be a pattern, all the molecules must be perfectly aligned with each other. If we were to heat the material above its melting point, the material would become a liquid and the molecules would be able to move about. The pattern would be lost. So when we say a material is crystalline, we simply mean it is a solid, and all the molecules it contains are arranged into a repeating pattern. You might say to me, hold on, is it possible that a material can be a solid, but its molecules are not arranged into a repeating pattern? And I would say, yes, we call that an amorphous material, and there is a separate video where I discuss those. What are the consequences of having all the molecules in a material arranged into a pattern? There are a lot. Imagine this Lego brick I am holding represents a molecule. I have put a sticker at one end to denote a particular functional group, let's say a carboxylic acid. The reason for this will become clear in a moment. Since crystallinity really means a repeating pattern, let's imagine how several of these molecules might be arranged in the solid state. They might come together in a pattern like this, and you can see all the molecules are aligned in the same way. How do we define the structure of a crystalline material? We could, for instance, record the positions of each of the molecules in space by assigning coordinates. That's fine when our material consists of only a few Lego bricks, but it's not fine for a real material, because even the smallest crystal will contain trillions and trillions of molecules, and our table of coordinates would become enormous. Instead, We look at the molecules and we ask, what is the smallest repeating block of molecules that tells us what the pattern is? In this case, we only need 2 of our Lego molecules. We can create our larger crystal by adding these units together in 3 dimensions. We call this smallest repeating structure the unit cell. By defining where the molecules sit in the unit cell relative to one another, we know everything we need to know about a crystal that we can see. We call these macroscopic crystals, because the unit cell simply repeats in each direction. Can molecules align in different patterns, I hear you ask? Great question, and the answer is, in many cases, yes. I have in my hand another collection of Lego molecules. Same molecules, but this time arranged into a different pattern. When molecules can arrange in different patterns, we call them polymorphic, and each pattern is called a polymorph. If you're following what I'm saying, you'll see that each polymorph can be characterized as having a different unit cell. These are the unit cells for our 2 Lego polymorphs. If we compare our 2 polymorphs, we can see some differences between them. In the first case, the molecules seem to be more closely packed than in the second. We would therefore expect the density of this polymorph to be greater than the density of this polymorph. Secondly, because the molecules in this polymorph are closer together, they have probably formed stronger intermolecular bonds than the molecules in this polymorph. Remember, when a material melts and changes phase from a solid to a liquid, we have to put enough energy into the material to break the intermolecular bonds holding the crystal structure together. So we would expect this polymorph to have a higher melting point than this one. There are many other physical properties that change between polymorphs, even solubility, but I'm going to discuss that in a separate video. Finally, I noted earlier that these stickers represented a carboxylic acid group. If you look at our polymorphs, you will see that in this form, because all the molecules are in alignment, all the carboxylic acid groups are at this end, or face, of the crystal. But in this polymorph, there are carboxylic acid groups on 2 faces. Because in a crystalline material the molecules are arranged in the same pattern, we have to remember different faces of a macroscopic crystal will have different chemical properties. This becomes important when we think about growing crystals, but that's a discussion for another day. So, what are the take-home points? When we say a material is crystalline, we mean that A, it is in the solid phase, and B, all the molecules in the material are arranged into a repeating pattern. We don't have to describe the positions of all the molecules, we simply look for the smallest repeating pattern, which we call the unit cell. If the molecules in a material can arrange in more than one pattern, more than one unit cell, we say it is polymorphic. Each polymorph has different physical properties, such as density and melting point. Right, I hope you found that brief description useful. If you did, please hit the like button and consider subscribing. It makes a huge difference to the channel. I will be posting many more videos explaining fundamental science concepts, and if there are any particular topics you'd like me to explain, please leave a comment below. Otherwise, thank you so much for watching, and I'll see you again soon.